So I want to jump into derivative shortcuts. Again, we want to go through these topics, remembering that the formal definition of derivatives is that it is an approach of slopes, right? The derivatives, by their definition, are a limit definition done on a difference quotient. In other words, they're the approach of slopes. It's a limit attached to the slope equation. And we've got a couple different ways we can represent that, but that is what we are talking about. And from that approach, we're considering approaches from one direction and the other direction. So for every one of these shortcuts that we are going to be showing, these are shortcuts that are backed up by that definition. These are not unique things. These are not extra details. These are a way of us trying to get to the answer at the end of all of that computation without having to go through all that computation, which is why I'm going to call them shortcuts. If you look up in your book, they will say that they are rules. There will be a product rule. There will be a quotient rule. There will be a chain rule. I don't like the word rule because rule makes you all think that you have to do it because I told you. And it's not about that at all, because it's not a rule. Like, no one's making us do this. It's a shortcut we are choosing to use because it will get us to the answers faster, not because it's something different. Okay, it's a shortcut. It's just a shortcut. So we're going to look at some of the basic building blocks that we use for functions, addition, subtraction, and then multiplication, and get some shortcuts for those so we don't have to do the limit definition each and every time. That means we're going to do a little bit of work now with trying to use variables and function notation so that we can save a lot of work later and not have to do all of that computation for each and every problem. We all feel like we got a good approach for kind of what today is going to be about? Okay, let's jump in. We're going to start with some of the easiest functions that we've all worked with, polynomials. Polynomials are awesome, right? Because from a technical standpoint, are they continuous? Yeah, they're going to graph a nice little curvy thing, right? No interruptions, right? Each of these are shapes, right? X grows as a length, X squared grows as an area, X cubed grows as a volume, and all of those change gradually as I change things. In fact, I can see that even if I sketch something here. If I say this is an X squared because it's an X by X object, and then I go over here and I, on my computer display, grab it, like, look at how gradually that thing changes. No interruptions, no sudden disappearing, no sudden I have no idea what it is or how big it is. So we've got a nice change, a nice flow that's always going to happen as we drag these shapes and we move them up and down. In fact, polynomial comes from roots where poly means many, just like I have many pieces here, and nomial refers to names, names of shapes, which is why we describe these often with shape names, right? We've got X squared and X cubes, even X to the fourth is a shape. It's just a shape that I can't draw with 3 dimensions. I need 4 because it's X to the fourth. Some people in physics might know that it's called a hypercube, or sometimes referred to as a tesseract. It's really just saying it's a 4-dimensional square. And then we have 5-dimensional squares and 6-dimensional squares. And some people say that our universe is 12-dimensional, so we can go up to 12 dimensions of squares. But even for our purposes, where we're training for industry, a lot of us, we can think of these as just being the result of multiplying. So that if I have many people working on the assembly line and each person is producing many products, then I've got a multiplication between the number of people and the number of products. That's going to cause there to be possibly some X squares, right? Because I've got multiplication. And I can make an X cubes if I talk about how many people I sell each of those products to, and I get some division and multiplication that result from that. Like, it's just an amount of multiplication that we choose to model as shapes. So polynomials come from a root talking about shapes like the ancient Greek geometers. But today we like to think of them more in an algebraic sense, where they're just the result of addition, multiplication, possibly subtraction. Does division come up in polynomials? Can we have X to the negative first in a polynomial? We cannot, right? Because we're talking again about that ability to build and that ability to not be interrupted. The moment you introduce division, we cannot divide by 0. So like, that's not the same category of functions. We're talking about polynomials are just multiplication, addition, and subtraction. Anything else we categorize differently, and we'll talk about rules for those later. Now, we did mention in the last class this idea of differentiability. Differentiability is the ability to find the derivative for a certain X value. We didn't get a chance to go into it with much details, but if we think to ourselves about a graph that is interrupted, we could ask ourselves if at that point of interruption, is there a derivative? Well, remember, derivative means the approach of slopes. So let's sketch some slopes and look at how they approach. We could come in here, we could draw, if I wanted to look at this point, I need to choose this point because that's one of the points I'm at, right? And I compare it to points nearby. If I compare it to this point that's nearby, I get a slope of 0. If I compare it to this point that's nearby, I get a slope of 0. And the next one would be a slope of 0. So from one direction, it's suggesting that my derivative will be 0. Now let's compare it to some from the other direction. I could grab this one, which is the nearby x value, and I've got a slope that is negative. And then I've got a slope that is more negative and more negative. So from this direction, it seems like the slope is becoming increasingly more and more negative. Well, from one direction, it's more and more negative, and the other direction, it's constantly 0. My derivative is undefined, does not exist. I don't have an agreement in my limits. I do not approach one thing, right? So what we realize is there's a nice connection here between being continuous and being differentiable. If I am continuous, then I might be differentiable, right? Like, for example, a graph that has a sharp corner is continuous, but is not differentiable. Because again, from one direction, I think I have a slope that's negative, one direction is positive, sudden change at that moment, not great. So continuous does not mean that I am differentiable. But if I'm differentiable, then that must have meant that I had a gradual incoming of change and a defined point to reference in the center. So if I'm differentiable, I am continuous. But if I'm continuous, I am not necessarily differentiable. Slight little play there. So differentiability is a more extreme condition. If I can have an approach of slopes, I also must have an approach of the graph. But if I have an approach of the graph, I do not necessarily have an approach of the slopes. We can play a little bit with some organization there. All right, when we're talking about the polynomials, though, thankfully they're both differentiable and they're continuous because all these things are changing gradually and they're all connected. That means that I can use some connection of the power rule and say every single piece of this looks like it's going to change as a result of the power rule. Can I prove that altogether it's going to be connected by the power rule as well? Or at least it's going to be changing overall as a result of how each individual piece changes? We would want to think yes. And in fact, we'd be right. Now it's a matter of proving. So we're going to start with two different proofs. We're going to start with, can I use the limit definition to show that if I have a constant times a function, like 5x squares or 5 natural logs of x or whatever, if I have 5 times something, is that going to be able to have a derivative where I just find the derivative of the changing part and then bring that constant along for the ride? Well, first we'll start about this from a story. If I said that I have 5x squares, that's a vertical shift in my graph, right? 5x squares grows a lot faster than a single x squared. So it's going to grow a lot taller. That means that I have much, much more rise. Well, if I have more rise, then if I look at the rise over run, we would expect that to go up, right? In fact, we'd think 5 times more rise because I have 5 times more height. And that would mean 5 times more slope because I have 5 times more rise from 5 times more slope. So it would make sense that as we make these things taller, the slope is going to get equally bigger. And that if we make them shorter, the slope is going to scale down by the same amount. Watch how we can show that by using the limit definition, because we've got to make this come from a place of formality, not a place of anecdotes. So we're always going to start off with trying to determine what this derivative is. And remember, this is a story through the notation. This says I am about to take the derivative of c times f of x. And I can do that formally by using the limit definition. Now, for some of the proofs that I'm going to show you in the next couple days, I'm going to be using the h goes to 0 version, although there would be an equivalent way of doing it with the b goes to a version. It's just that the h goes to 0 simplifies a little faster and is a little bit better for our note taking. So I'm going to use that as a representation, and you all are welcome to use that way for solving number problems. Or you can use the one that's my favorite, which is just b goes to a. And for numbers, it works out just the same. Like it simplifies just as quickly. But for variables, it becomes a little bit more difficult to balance. So I'm just going to use this version, even though it's my less favorite, because it's a better presentation to you all. So we're going to start off with this limit as h goes to 0 of f of x plus h, which is my later height, compared to my earlier height, f of x, divided by the run between them, which we called h. The difficulty is that in the first problem, I'm plugging in an x plus h to everything, and then I'm plugging in an x to everything, and I'm doing a comparison. Well, plugging into everything means that I'm plugging in x plus h from here, and I carry the c. So I technically need to have c's here, right? This way, it's like I plugged in the x plus h to the entire thing to get a rise later. I plugged in an x to the entire thing to get a rise at my reference, and then I've got a run between. Do we all feel all right on the setup here? Well, this one's going to simplify quite quickly then, because what we can say is that the limit as h goes to 0 is going to be the same thing as c times f of x plus h minus f of x all over h. Notice that, by the way, through here, this is not just symbols, this is a story. This says that if I scale up my function, then the heights I use for calculating rise will scale as well. That's what we had already discussed. And you can see that right here, right? I have c times the height. I have c times the height, which means I have c times the difference of the height, c times the rise. That's what we had discussed. As the heights go up, the rise goes up. And then I can say if the rise has gone up and it's gone up by a constant, as h goes smaller and smaller and smaller, c doesn't change, c is a constant. So I can bring that out in front. And I can identify that that last thing is just the derivative. So now we're able to show this in a way where no one can argue with us. So we've been able to use the definition of the limit, or excuse me, the definition of the derivative that has a limit, no anecdotes, and simply show exactly what we thought through our intuition, that as the heights go higher and higher, or are scaled possibly lower and lower, that's just going to affect my rise, which affects the numerator in my slope, which affects me being that much more times my slope. And we've just shown that with our symbols. Any questions here? Feeling good? Okay. The next one is going to be a little bit more, but it's not too bad. Now we need to figure out what happens if I add two functions together. Well, we can think of this graphically. If I add two functions, then at every single x value, I'm adding two heights, possibly some subtraction, right? If it's adding a negative height, that might be some subtraction. I'm going to say adding loosely, and you could just think of it as possibly being the addition of negatives. But like, I'm adding heights. If I add heights, will that affect my rise? I've got one person nodding. If I add heights, does that affect my rise? Yes, absolutely. If it affects my rise, should it affect my slope? And wouldn't it make sense that it would affect my slope by adding that much more slope? We're just going to show that again through our symbols. So we're going to prove this derivative again by starting with the limit definition. Again, the h goes to 0 one just works out a little bit better for this proof, and it's the one that I've got memorized in my head. So we're going to plug in this x plus h, but we've got to plug it into the entire thing since we're considering how the entire thing grows. So this is the height of the entire thing later minus the height of the entire thing earlier. We all feeling good that, again, all I've done here is use the limit definition, and I plugged in those later x values, and I plugged in that earlier reference x value? So if I want to make this be in terms of F's derivative and G's derivative, that means I need to group all the F stuff together until it looks like a derivative, and I need to group all the G stuff together until it looks like a derivative. So that's exactly what we're going to do. So I get the f of x plus h minus f of x when I distribute in that negative. The next part is going to be probably some symbols you haven't seen before, but we'll understand where they come from once I write it and look back. Does it make sense that I could essentially factor out a plus or minus? Let's double check. Plus or minus, if I distribute that back into the g of x plus h, I get plus or minus g of x plus h. That looks like what I had earlier. And if I distribute it to that negative g of x, that would be the opposite of plus or minus. What's the opposite of plus or minus? How about minus or plus? Right, same idea, but it's talking about it would be the opposite of whichever of those plus or minuses I had. And that's exactly what we have here, right? The negative of plus or minus g of x would have been the negative of plus or minus g of x, which is minus or plus g of x, which is exactly what we have right here, right? The plus or minus times the negative is still captured. Still captured. If you ever want to write minus or plus, you can write it like this, by the way. Super fun. All right, either way, it is still equivalent, so we're good to go. Once I've got it as two different fractions, I can make it explicitly be two different fractions. Sometimes in our notes, it's a little difficult to keep track of the fact that the limit is still applying to everything. So you're always welcome to add some parentheses here that kind of remind us that the limit is for everything. And if I look at that first fraction as h goes on down to nothing, that's the derivative for f. And if I look at the h going down to nothing for the second, that's the derivative of g. So we've now shown that when I do that limit, I get the perfect slope at x for f, and then plus or minus the perfect slope at x for g, and we're good to go. I always find it a nice challenge to go back through these equations and try to give meaning to each of the steps in there. Like, for example, when we read the first one, that was saying I've got a total function that is combined from both g and f, and I'm looking at its later x value compared to an earlier x value. That's fine. In the second one here, this is saying that I equivalently could look at how much f grew in that time and how much g grew in that time, and so that should be the same as how much f and g grew in that time. And it's like, yeah, that makes sense. And it's like, well, then if I look at how much they rose and I compare that to the same unit of run, then I get a discussion about how each of their slopes were during that time. And we find out that their slopes added because their heights added because the functions were added and everything is nice and cohesive. Right? Kind of make it not just symbols on paper. Any questions here? So for our purposes, what this means is that we can now tackle doing the derivatives of polynomials really, really quickly. We don't have to throw polynomials into the limit definition anymore. We've just found shortcuts that are true for any function. Polynomials, logarithms, trig functions, all of them are represented in what's in front of us here because all of them would flow through the limit definition the same way I just had f and g flow through it. So we can now use this shortcut and not have to rely on plugging things back into the difference quotient. For example, let's play with this one here. So I want to do a derivative of each of these pieces. Now I'm going to show you the long, drawn out, really thorough way of showing those shortcuts. I'm going to put it in brackets, and then I'm going to show you what I'm actually going to be expecting from you on a test, which is for you to do this in real time, right? Real time as we flow through it. So if I wanted to make this super formal for my very first notes, I would say if I wanted to do the derivative of all of this through the addition and subtraction shortcut, I know that I can do the derivative of each individual piece. So I would write that nice and explicit. So that's through the addition and subtraction shortcut. And then we could use the power rule for each of those individual pieces, right? But in fact, the power rule doesn't talk about the number in front. Well, technically it does, but now we even have a shortcut that backs that up more, that the number in front can be thought of as just a constant. So we could even make this a little bit more explicit. We can make this one will be the same. But this next one will be the same thing as negative 22 times the derivative of just the x cubed. And then we could go through all of this with the power rule, right? We bring those powers to the front and we decrease them by 1 because we're doing derivatives. So at this point, I'm going to kind of take all this here and I'm going to section it off because this is the behind the scenes super overkill justification to show you how all those shortcuts come into play. What I'm expecting from you all on the test and for you all to be able to do on your homework is I expect you to do this in real time. That we just go piece by piece and say the first thing has the power rule, so the 7 comes down, I decrease it by 1. For the next one, I have the power rule, so the 3 comes down, I multiply to 66 and decrease it by 1. The 2 comes down, I get 8 times x, decrease it by 1. And then I bring the 1 down, I get negative 6, x to the nothing. And then what's the derivative of 5? 0. So there we go, we box it, we're done. One line of work. Boom. In contrast, imagine plugging that thing into the limit definition. Oh my golly, like we got x plus h's being distributed. Maybe it'd be a little bit nicer if we did the b approaches a definition. Maybe some more things would cancel. We'd still have to do quite a bit of factoring and FOILing and canceling to get rid of that divide by 0 error. And like, just no, right? The value of shortcuts is once we prove it once formally, we never have to do it again. Love it, big fan. Now, keep that in mind that like on the test still, if I ask for the limit definition, you need to show me that you have the limit definition understood, because being able to do shortcuts just puts you in the same category as being able to act as a calculator. And I already have calculators, and they are a lot cheaper than you, right? So do not leave here with the ability to just do what my calculator does. Leave here with the ability to explain to me why what my calculator got makes sense, right? That's the skill set that you're trying to grasp. Products, multiplication. Now, it's at this point when we've got to kind of hold back that temptation of saying, well, if I have a constant and I'm doing a derivative, I can just multiply the way I would think. And if I have addition and subtraction for derivatives, I can just do addition and subtraction the way I would think. We could ask ourselves for products, is this going to be the same thing as looking at how much f changes and then just multiplying that by how much g changes? I mean, we would think, right? Do the derivatives that are in front of our eyes. But this becomes the very first time when we want to be very careful that what's in front of our eyes is not the name of the game, right? Math is a model of logic. We want to make sure that this is justified with logic. And right now, there's no logic here other than I saw a delta and some stuff. So I decided to do delta of some stuff. No, bad logic, right? So instead, we want to kind of explore this story. Thankfully, I've given you one of the most persistent models in this class. If we're talking about multiplication, how do I draw that? I love rectangles. Rectangles are great. We should use some rectangles here. Let's play with some rectangles. So let's use some rectangles. If I want to talk about multiplication of functions, though, just understand that these are no longer rectangles that have numbers on the side. They're rectangles that have variables and functions and operations on the side. So we're talking about something that's allowed to dynamically shift and morph, that like the width might get longer and then the length might get shorter, but then the length might catch up and get longer, and then the width might stall out and stay at its point for a certain amount, right? Like we've a big fluctuation of changes all based on stories and functions, and we don't have to worry about those details. We just have to understand that they're there. So let's try to sketch out what this rectangle is going to look like. I'm going to start off with a rectangle that just exhibits the multiplication. So I've got f on one side, I've got g on the other. I'm going to choose not to write the of x. I just want you all to remember that it's there. But since I'm going to be playing with multiplication and parentheses and stuff, I don't want people to get distracted and accidentally visually think that the x was a multiplication I was working with. So just understand that you can add the of x, but these are functions. I'm just going to make them f's and g's for the purpose of easily presenting it. Okay. Now, if I change f, that's going to change my rectangle's width here. So I'm going to sketch that in right here, change f. Do I know that just because I change f, f gets bigger? No, not at all. It could absolutely get smaller, right? But just like we worked with in our visual algebra, I can think of like negative regions, and that's totally fine. It will still work out for my area overall. We'll just say that now I'm changing by increasing negatively, right? And that's totally still going to work out. But for visually proving this, it's helpful if I just kind of show it as growth away. For g, we've got g, which is also allowed to change. Again, it could be changing inwards, but the moment I do it inwards, the picture becomes cluttered. So just imagine that it's changing, and it could be changing negatively. Well, similar to like our x squareds, right? If I have something that is 10 by 10, and it increases by 1 on each side, does that mean that it's now just that? Just the interaction of the growths? No, it'd also be the corner. And in fact, we can see that that's exactly what happens, right? It goes from being 100 to increasing 10 on one side, 10 on the other, and then 1 in the corner. Even if you made it negative, right? Even if you said it shrunk by 1, as a reminder, it could be still done with this picture, right? It shrinks by 10, 10, and then grows by 1. And you can double check that. Is it true that a 9 by 9 rectangle is the same thing as 100 minus 10 minus 10 plus 1? Yeah, right? Because you can think of it as like if I bring in one side, then I kind of like take away that corner along with it. And then if I bring in the other side, I take away the corner along with it. But then I've taken away the corner too many times, right? One too many times, and I need to bring that corner back. That's exactly what this says. It says that I took a shape, I decreased the two different sides, but in doing so, I double counted the corner, and I need to make sure that I account for that. So that's what we're talking about when I'm drawing this figure. It can change negatively as well. It's just a drawing. All right, so then this one's going to change similarly. I've got a whole new swath of region here that I've created, and the areas are going to be g times delta f. I've got f times delta g, and I've got delta f times delta g. So if I now go off to the side, I can say that the area has changed by these three different regions. The region that is g times delta f, the area that is f times delta g, and the area that is delta f times delta g. So now we start to recognize that changing through multiplication involves a little bit of an area model, that we have this kind of give and take. We've got this interaction effect that's playing around. Since I ultimately want this to get back to how am I changing things as a result of changing x behind the scenes, let's start to make this look more like our derivative. Let's start to divide everything by delta x. We'll compare how everything changes as a result of changing x. Little simplification. It doesn't matter where we put that delta x for the very last term, right? We can simplify it either way, and either way it's going to support the same result I have in a moment. Because in truth, the picture I've drawn for you is much too large. Derivatives are changes in a moment. But if I draw that, it's difficult for me to draw it in a way that appears well in the picture. We could think of it a little bit as saying that change in the moment is going to be more like me changing it so that it's very small change, very skinny change where I just sort of have a small little layer here, a small little layer here, and then a dot at the corner. So it's like I want to look at the limit as I cause this change to become smaller and smaller. So we could write that off to the side as well. I'm going to do the limit of everything as delta x goes to 0. I'm going to consider how I'm changing moment to moment instead of big steps and big steps. Well, if I do that for this part over here, that's the small change in area, very, very small change in area that results from a small change in x. And then I get g times a small change in f ratio to a small change in x. I get f times a small change in g to a small change in x. And then off at the side, I get a small change in f times a small change in g ratio to a small change in x. Let me pause here for a moment. Do we all feel pretty good on this whole idea of me trying to change the things moment by moment instead of large step by large step? Because again, remember behind the scenes, it's no different than if I'm here on PowerPoint and I select this thing and I'm trying to change it. I don't want to compare change by looking here and then looking here. That's too big. I want to look at it pixel by pixel, moment by moment, how this thing is growing, right? Pixel by pixel, moment by moment. Let's pause here for a moment and take a look at this picture that I've drawn that's just a super skinny version. We can all see that this length right here, this has size. Do we all agree this has size? What about this? Does this have size? What's the size of that? What's the size of a point? When I bring this all the way down so that it is forever skinny, those two long things become line segments, and those have length. How big is a point? It's 0. See, this brings in our limit reference of saying, like, as df becomes very, very small, so does dx. And small number divided by small number has a chance of having a settle, right? Right. Small change in height, small change in run, still could give me a number for my slope. But what we see is in this very far corner over here, even if the dg and dx are able to ratio out to be a number, I've still got another infinitesimal there that's being multiplied in, which we know infinitesimals aren't even actual numbers. Like, what's the real equivalent of infinitesimals? 0, right? So even if the super small over super small fractions ratio out, it's still times a 0. So this is a number times 0, which explains to us again, like, why this has no size. Like, it's just no size. Moment by moment, it contributes nothing, which again is a little counterintuitive, that this thing never grows in the corners. It only grows on the edges moment by moment. At every single moment, we are simply changing it on the sides. But again, we can see if this kind of makes sense, because again, remember that what's the derivative of x squared? 2x's, right? Where x is a length. So that makes sense that the change in an x squared would be 2 changes of length, like we've seen this before. Similarly, we've seen it when we were talking about how do we change the area of a circle, right? The area of a circle changes by one more layer of the onion. that goes around just the circumference. So we're looking for just how do I build this next similar shape? And as it turns out for squares, their entire magnitude of area increases just because of the length on the edge. That corner, although I can draw it, has no sides. Well, all this together means that now I can come back here to my derivative and I can say if I'm trying to figure out how an area changes, it's just the first function left alone times the derivative of the second plus the first function left alone times the derivative of the first. I think I said that backwards. It's a derivative of one times the other left alone plus the derivative of the first with the other left alone. Like that's what it comes out to be. Now this is pictures, this is analogies, this is kind of diagrams, but this is all backed up with the limit definition. It's just that the limit definition has a couple of points that are a little not intuitive. So I provided them for you in the guided notes. You can see that the limit definition backs up what I have shown you here. But I want to give you a picture that can stay in your mind so that if you ever get stumped on a test or on a homework problem, you can remember that it's not as simple as just saying I do the derivative of the things in front of me, that there's this interaction effect that we have to account for. I want to pause here for a moment. Does anybody have any questions on this? You can start to see that it has a similarity to at the beginning of the semester when I was talking about how much space does the rational numbers take up on the number line, right? And that ability of being able to cover it with less and less and less and less stuff. Here, how much space does that corner give me? Well, I can keep covering it up with less and less and less and less until I conclude that it must be of zero size. And then similarly, we can talk about that for any of the limits that we've ever done, that if things are shrinking without bound, that they must be zero, versus the edges, the lines on the edge, those things are bounded. They don't ever get smaller than those line segments. So those do have length. The point does not. Lots of parallels. All right, so moral of the story, think of this picture, confirm and prove it with the limit definition that's provided in the guided notes. The limit definition there is pretty easy. There's one thing that you got to bring in that's a little not intuitive, and there's a lot of simplification, and it just takes too much time. And I want us to instead look at how we can use this, give some hands-on application. So on that note, let's do some problems. Let's play around with this one here. Anybody here into cooking? Anybody here enjoy cooking? All right, anybody here heard the phrase mise en place? I got into cooking. I got into cooking a while ago. I heard this phrase. Here's the general idea. If you're trying to cook an ornate, intricate meal, then the guiding wisdom is that you should prepare all of the things you will need at the beginning, right? So you should chop up all your vegetables. You should get all of your measurements made. You should be all off to the side, make it all out on the counter looking like a nice cookbook photo, right? And then as you are cooking, you pull the things in that you need so that you don't get to a place where the burner is on, you're actively cooking, and you go, oh, I forgot to chop the garlic. And then you've got to run off and chop the garlic, and then things burn, right? So you have to have everything nice and prepped and laid out to the side. For the derivative shortcuts, I find that incredibly useful as a model. So I strongly recommend that you do the exact organization I'm going to show you until you begin to be able to think about it in real time. And then once you can think about it in real time and have shown that you can do it in real time on the homework, right, to yourself, then feel free to start, cutting some corners and not writing as much down. But I strongly recommend that you go through every deliberate step that we're about to see. Because what we have here is we have two things being multiplied. Let's give them some labels. Maybe I'll call this thing G, and I'll call this thing H. So off to the side, I could think G of t is the square root of t, and h of t is 3 minus 6t. Now there's multiplication happening between g and h, which means that I need to be thinking of the product rule if I'm going to do the derivative. So I might as well prepare off to the side all of those derivatives that I'm going to mix and match. So we could do the derivative of g. Who can help me with what that would be? What was it? Walk me through your thoughts. Walk me through your thoughts. Y'all are doing a lot in your head. Walk me through your thoughts. Good. Let's make it not -1. 1/2. Very good. Right. Let's make that explicit on our paper. I like to make that again, like especially on a test. There's rushing. There's time limits. There's stress. We're all tired. Right. So it's like put as much on the paper so your eyes can assist your brain. Otherwise, it's all on your brain, and that's just not a great recipe. So if we put it like this, now we can use power rule. That's probably what you're thinking of, right? Walk me through power rule. Very good. The power comes on down, and we decrease this to -1/2. Good. And then I have h prime of t. That again is going to be power rule, but it's power rule with each individual piece because we have the addition and subtraction support for this. That's going to be the derivative of 3, which is 0. Constants don't change. And the derivative of -6t is -6. All right, so I've got -6. In fact, I could just write it as that, right? So now if I want to do the derivative of this product rule, I'm just mixing and matching, right? Derivative of 1, original of the other, original of the first, derivative of the second. I like to think of it through a little limerick where it's just derivative of 1 times the other plus the derivative of the other times the first, right? Something of a little bit of a rhyme here. But really, we're just mixing and matching. We're doing that interaction effect. So I'm going to first do g times h prime plus g prime times h. And then I've got g as being t to the 1/2. H prime, I just grabbed from what's on the left, -6, plus g prime, which I again grabbed from what's on the left, 1/2 t to the -1/2. And then I've got times h. That's the derivative. Could we simplify? Yes. Specifically for this class, look out on the tests. Sometimes because on the test, we really want you to have a chance to show your work on a variety of problems, we will give you permission and say, do not worry about simplifying. Because we trust you can simplify for that problem. And we really want you to have time to do the other harder problems that take up a lot of time. So if I give you permission on a question that says, do not simplify, don't worry about it. Feel free to just kind of leave it at this point, box it, call it. If I don't give you that permission, then you should simplify. Because simplification is a way of us being able to find patterns that connect things. For example, have you ever seen this as an answer to a question before? Look super familiar? Maybe, maybe not. What if I did a little bit of a rearranging here? What if I made that be that? Have we all seen that before? Oh, yeah, right. Unit circles, trig, stuff is flowing. So we simplify to make it easier on our brains to connect patterns so that we can look back at models previously and understand like, oh, maybe there was a unit circle that is behind the scenes in this problem, right? We simplify for that reason. But if I give you permission not to, then you have permission not to. Every year, the final exam comes and it has these questions and the coordinator says you don't have to simplify, and then dozens of students waste tens of minutes simplifying. And we're not going to give you credit for that because we told you you couldn't, like, didn't have to do that. So just read instructions, I think is the moral of the story. All right, but if we did want to simplify this, this would be -6 times the square root of t plus, and then this one would be what? 1 times 3 minus 6t divided by 2 square root of t, and then we could do common denominators, et cetera, et cetera. For our purposes right now, let's just say that's good enough. So again, as a reminder, although I like this picture and this picture is true, and this picture is like the model I would like you all to use as a reminder that you cannot just do derivatives of things in front of you and then multiply just those derivatives. It's not true because of my picture, it's not true because of my story, and I skipped a lot of details and loosely threw limits around, right? This actually is provided for from the limit definition. Like you need to do this from the limit definition. So the limit definition, as I said, is in the guided notes. It does require a little bit of creative strategies for how to make the numerator be something that simplifies with the denominator and reorganizes around. So just understand that at the end of the day, we're still formalizing derivatives using the limit definition. Stories are now no longer the thing we rely on for understanding. Formulas and definitions are the things we rely on for understanding. Now, I want to show that we don't just have to deal with this in terms of two things being multiplied. We can actually do it in terms of three things being multiplied. It's no more difficult. It's actually just as easy, so long as you adopt the organization that I was showing you last time. So let's take a look at that today before we get into the new material. So we've got the product rule up and to the right. Product rule is saying that we've got the derivative of one thing times the other as is, plus the derivative of the other thing plus the first as is. And we've just got this mixing and matching pattern. Well, the question becomes, what if I have three things being multiplied? Like I've got f being multiplied by g being multiplied by h. Still, I would say let's tackle this problem by just kind of recognizing that we could find two things being multiplied here and then begin our analysis like that. So let's start off with giving them some labels. Big fan of labels. Let's maybe call this thing maybe P for product, and we can call this one Q because it's the letter that's after P. I don't know. And we can go up to the side here and just kind of create our mise en place, right? I think that translates to mess in place, which is a weird translation. But nonetheless, like we're just going to get all our ingredients off to the side and begin to prepare our large recipe. So we've got P of x, which is f of x, and g of x, and q of x, which is h of x. I could also have just like relabeled this and made the other thing be the thing with two different functions in it and the other one with the one. It doesn't really matter. Like that's not the point. The point is that it's just multiplication. And so now if I want to find the derivatives, because I know I need to do a mixing and matching, how would I find the derivative of P of x? Yeah, it's the original product rule, right? Now I've just got two things being multiplied together. So let's just do a little mix match. So I've got f prime g left alone, f left alone, g prime. And then for q prime of x, that's just the derivative of h. And so now we're just going to do our mismatch, right? I like to do a little setup here just to make this nice and clear for the audience that we are going to be doing it as p prime times q as is plus p times q prime. And now I'm just grabbing everything off to the side, right? Grabbing it in, pulling it in. So I've got p prime, I'm just grabbing it from what I have on the left. That would be a big old thing of f prime of x, g of x, plus f of x, g prime of x. And then I need to grab q, that's just h of x. And then I'm going to add that to p of x, which is f of x, g of x, times h prime of x. A little simplification. And now we take a step back and we notice that it's again a pretty similar pattern. It's a pretty similar pattern to what we had above. I mean, take a look in the first one. We just had the derivative of f, everything else left alone. Then we had the derivative of g, everything else left alone. And then we had the derivative of h, everything else left alone. So this idea of a product rule just being the derivative of one times the other can now get extrapolated a little bit to say, no matter what you're multiplying, if all you have is multiplication, you're just doing one of their derivatives, leave the rest alone. Plus the other thing's derivative, leave the rest alone. Going down the ladder each and every time until you've got a term that has everything's derivative accounted once with everything else left alone. The product rule is a really, really nice pattern that extrapolates to more and more things being multiplied. Yeah?
Is there a situation where you have more so many variables that
Nope. Nope. This actually continues on and on and on. So even if you have four functions being multiplied, you do the product rule by saying derivative of the first function, all the others left alone, derivative of the second function times all the others left alone, et cetera, until you've exhausted. Now we can see why this is if we again go back to that model, that visual model, because when I had two things being multiplied, I got a rectangle. If I wanted to model three things being multiplied, what would that be? It would be not necessarily a cube, but it would be a three-dimensional rectangle or a prism, a rectangular prism is what it's called, right? A box. We could just get a box, right? And if I wanted to look at how that box changes, let's just do a little sketching. Here's the three-dimensional box, right? I just don't want to call it a cube because they're not necessarily all the same size along the lengths, right? But if I, again, adopt that idea of I'm just trying to change this into something bigger, then just like through PowerPoint, right, I can grab this thing and I can say I want to just make it bigger. When I've got it bigger, I'm just dragging it in terms of those three dimensions, right? I'm just trying to make one side bigger, the other side's bigger, the third side bigger. Well, I can sketch that in. If I make this side bigger, then I've added kind of a sheet against that layer. And if I make the other side bigger, it's like I'm just making that side bigger. And I could do that for the third side as well. Which again reminds us that behind the scenes, we've got the idea of anything that is of x cubed orientation, the derivative of x cubed would be what? 3x squares. Oh, and look, it's like we've got an x square, an x square, and an x square, because that's how I change things that are cubic in size, is that I change them three ways against their largest surface. Now, if you did this like perfectly geometric, there'd also be little slivers along the corners here. And it would change right at this corner as a dot as well. But as we saw in the last example, if you do all of those ratios and you look at how things change as a ratio of x, like the largest size contributors are going to be on those three faces, and all the rest of them are insignificant. And you can feel free to kind of play around with the infinitesimals if you want to see how that intuition works out. But otherwise, it's just an extrapolation of the last picture. This thing is changing in majority based on those three faces, and all the rest of them are inconsequential. Because let's look at the dimensions of this one. If I say the dimension of this one might be f times g times dh, right? Because it's a length along f's side perhaps, and a length along g's side perhaps, and then a tiny little depth that's created by dh, like a change in that last dimension. If I now ratio this to a small change in x, then I get f left alone, g left alone, and then the derivative of h with respect to x. That's just like this term. If I look at any of those other pieces of growth, they would have two infinitesimal dimensions. And even if I ratio them to dx, one of them will turn into the derivative and the other one will run off to zero, which cancels out everything. So again, like there's some intuition there. If you're interested in a video, a nice graphic that explains this, shoot me out an email. There's a YouTuber by the name of 3 Blue 1 Brown who does some really, really wonderful animations for calculus. And he's got a great animation for how this thing grows three-dimensionally and how when you shrink it, those lines and point segments become inconsequential. Cool. Anybody have any questions on how we can tackle doing product rule with three or more things? You all right? Great.